exercise 53. So in the previous exercise 51 and 52, we discussed about those exterior algebra or exterior power, particular those related with differential forms. Let's quickly recall the definition. So in different settings, sometimes we call the same thing slightly different. So at the M, it's the loose manifold. We denote tangent space of M at point small m by T and big M tangent space, which is vector space of all linear derivations germs P smooth functions. Denote du call it the cotangent. This is the du space of this vector space T tangent space TMM. So this is the du space. We call this du space the cotangent space. Of M at small m. Still under the assumption M is a smooth manifold. So notation here is slightly different. Usually we put wedge. We put this K on the superscript, but without confusion, let's see the notation here. All the points of M, we get all the exterior power of tangent space at P. This is vector space. This is its extra power. We have defined all those, and then take this joint union. And we call it gamma k star m. Call it exterior K bundle over M. Similarly, without putting this K, this exterior bundle. Over n. And so what is this? So this is defined to be the disjoint this, but this is graded algebra. Obviously this k should be bigger or equal than 0. So the obvious projections. And the corresponding sections called differential keyform. Let's say pi from, so you have your manifold M. Now for each point P, you have this either gamma k TPM or gamma TPM, depending on which one you're talking about. Right, then you have all those like a vector bundle, and so this projection is pi, right? We call the infinity section of this bundle gamma star n or gamma k gamma star kn. So let's be consistent. So let's put this okay, let's write this way. The cross section of this differential form or a differential key form. So what we do is a section would be, I'll put this for each point. You have to find an element in its tangent space, right? So let's see. You have make all the choice. So we give this section and you give something vector field. This is a key form. And we further the set of all differential k-forms of M as omega k of M. Note that omega 0 of M is a vector space of smooth functions. So differential zero forms, which means differential zero forms would mean the intersection of this gamma 0 star n, gamma 0 star n corresponds to the section of the disjoint union of gamma 0 tangent space. And the gamma 0 corresponds to those functions, continuous functions. And so on each tangent space, there is, you choose that continue, you choose vector there, and then they form altogether a continuous function on this manifold. Given zero form, a smooth manifold, for some point on it, is differential at the point M is a linear map. It's denoted by dfm from the tangent space point M, row numbers. Which means you start with f, define what is called differential at point M. Actually, what we really do is we can define what is df which maps this M to that dfm. And this df can be considered as a one form on N. Another thing to recall is that singular simplexes so the standard K simplex denote delta K is defined to be K equals 0. This is just 0. And for K positive, this is the subspace of Rn consisting of all those xi summation is equal to 1. So for example, if I'm working with R2, this would be all those x1 plus x2 that's equal to 1. So x2 that's equal to minus x1 plus 1. So, and x1, x2 positive corresponds to this triangle, as you could imagine. So if you got R3, so corresponds to this. Tetrahedron. And then for a differentiable manifold, differentiable singular K simplex is defined to be a map. Let's call it sigma from delta K to M. So from this very standard and very rigid space into your manifold, which extends to C infinity, mapping on neighborhood of that. Call this K simplex simply. Okay, just call this K simplex. And then we take all formal linear combinations. Let's say with real coefficients. Of K simplexes, and to know this set of or formal linear combination of K simplexes by S, and so K simplexes manifold at real coefficients. So element So this vector space would be of the form AI sigma I. So this is for more linear combinations of k-simplexes. We'll define what is a k-simplexes. K-simplexes is sigma from delta k to m, so this is a linear combination of those. So the sigma I is a k-simplexes. AI is a real numbers. Right. And so we call this K chain. And if you don't mind with this K, take all the such chains denoted by S star. One can define an operator on simplexes. Let's say partial with sigma defined to be summation minus 1 sigma I. Where the sigma I in the I space of sigma. And so this is actually what you do is start from sk, applying a partial, you got to sk minus 1. This is differential operator on chain complex. Now let's talk about cohomology. So again, M smooth manifold. We'll define what is this differential form. With exterior derivative. I haven't really described this, but this is standard. We can have complex. So this is a chain complex. Sorry, this is a cochain complex. And we call the corresponding cohomology De Rham cohomology of this differential of this smooth manifold, and denoted by HQ De Rham. De Rham cohomology group. Similarly, one could, as what we have described, we have cochain complex using this k-simplexes. corresponding Q's homology, we call it Q's singular homology, denoted by mentioning the coefficient R. De Rham cohomology, singular homology, and De Rham theorem will give a relation between these two. So we're talking about Q's homology, but let's still mention that there is a cohomology version. We define this superscript K to be the due of the homology version. And correspondingly, we define this partial R to be the dual map of the partial there. This induces so similarly such a map. Okay, I call this cohomology singular cohomology group. To be the De Rham cohomology and the singular cohomology we want to compare. So this exercise is here. Show that let's just compute the simplest smooth manifold, which is 1 point. Show that the De Rham cohomology of this single point is isomorphic to the Q's singular cohomology of the single point, and further isomorphic to R, Q equals 0, and vanish for Q not equal 0. Okay, just by direct computation. Let's start with the De Rham cohomology. So this 1 point space is 0 dimensional. And all maps of most over it so this 0 dimensional implies that this K forms. So because if your K is bigger than 0, then you go into repeating and the wedge will be trivial. So this is 0 for all K bigger than 0. And omega 0 corresponds to all the continuous smooth functions on it. Okay, all the functions which will be just R. So the only differentials, look back to, so everything here will be 0, and so the only non-zero thing is here, and that homology would be isomorphic to itself, which should be R. have this omega 0 with a set of functions with a single point x, which is isomorphic to R. So therefore we have this De Rham cohomology isomorphic to R, degree 0. And then let's look at the singular cohomology. Let's start with the homology. And the cohomology actually, after we compute each degree, compute each term of this chain complex, well, I'll see that the cohomology could be computed equally. So there is only one K simplex into the space 1 point. Recall this is sigma from delta K to your manifold, but the manifold here is just this 1 point x, so this is a constant function. So a set of K chains which we denote as K X R. This is the R linear combination of all those K simplexes, but there is only one, the constant one, and so all those will be just scalar multiple of that one, so it will be one dimensional. Similar reason, this is telling you that cochain is also isomorphic to R. I mean, when K is bigger or equal than 0. Now we are going to look at this as K. This one, right? We're looking at this cochain, sorry, this chain complex. So isomorphic to R. I have to look precisely on those differential. So when K is bigger than 0, recall this is but notice its face is again just this constant map, right? Its face is again a constant map I mean all the sigma I are the same. Since there is only one constant map, therefore, as a conclusion, this would be either 0 or that map. Depends on your even or odd. When the degree is odd, it is a 0. While it's isomorphism. When the degree is even. And this implies that this is the 0. And then let me write this is isomorphic. So this is isomorphic to R because the kernel cushion image is isomorphic to R. This is 0 and k is odd. Because you have isomorphism, so the kernel quotient image isomorphic to 0. And if you write one more term, this is still 0 and it's even. So this kernel image is R quotient R, and this is kernel image is 0 quotient 0.